Hello everyone, so for today's topic, we'll be discussing the application of Newton's laws of motion. Remember that during the first half of the semester, during the midterm, we have discussed the concept of the Newton's laws of motion. So now let's talk about its application. Okay. So for today's topic, we'll be discussing the free body diagram, the frictional force on flat surfaces, and will differentiate the types of friction and solve problems involving friction. What is a free body diagram? When we say free body diagram, okay, of course we have this object, okay. This is a visual representation of forces acting on the object, okay. So we have to write all the forces or draw all the forces acting on the object, showing the correct direction of these. Remember that force, okay, force is a vector quantity, so it needs a direction, okay. And later on, of course, we'll be working on the total force or the net force acting on the object. See, for example, this one, of course, it is being pulled by a string, okay. So we have this force, of course, and then there's the frictional force on the surface of the object. So if this is the motion of the object, of course your frictional force is moving that way, and of course it has its normal force, and we have its weight, okay. So here you have to draw all the forces on the object, acting on the object, for you to determine the net force, okay. Free body diagram is also called the force body diagram in some books or some sites, okay. Most of the time will be, when we say FBD, you know what we mean by this, okay. It's the free body diagram, okay. So next, this is an example of a free body diagram. Look at this. So here the man has several forces acting on his body, of course. We have the applied force, normal force, another applied force, of course, the frictional force if, of course, his shoes touched the ground or the floor, and then, of course, the pull of the gravity, which is the weight, okay. So here's the free body diagram. It's actually drawing all the forces that will be meeting at certain points. Say, for example, this is the point where all the forces would meet, okay. But here in this example, we have the frictional force and the ground, of course. This is another body, but if we'll be looking for the force on this body, the runner, we have here the air resistance towards west, so here, and then his applied force, of course, towards right. And then because it has its weight, it also has its normal force. So this is your FBD, okay. Next. So as you can see here, we have an inclined plane. So if you have an inclined plane, of course, there will be an angle. Okay, this is your angle. Okay, 30 degrees. And you can see that some forces is also inclined at an angle. So of course, if we have an angle, remember that we have our components, okay. So you can compute for the components of that. See, for example, this is the weight. So this is your this is the weight sub x, okay, or sub y rather, and this is the weight sub x, okay, along the x component. So, and this is the weight, so there is component, okay. So in this example, these are the forces acting in this. We have the normal force. Remember that the normal force is perpendicular to the surface. That's why we have the surface, so the normal force goes this way, okay. So this is the normal force. But if it rests on the floor and this is your surface, so this is the normal force, of course, perpendicular to the surface, okay. So then later on, you will be working on this for you to find the net force, okay, the summation of forces. Okay, another example. If, for example, you are like pushing this grass remover. Okay, so we have here this. Let's add. Okay, so here your applied force is going this way. Okay, if of course there should be a meeting point, so forces, so we have this point, and this force pointing downward will be drawn here. Okay, because this is the again the origin. So we have the normal force, the weight, okay, and the frictional force, and then the applied force. Okay, so next. Okay, so for free body diagram, it would make sense when we are solving tensional force and of course frictional force. Most of the time it will be solving problems involving forces. Okay, so you have to draw your free body diagram or the FBD so that you'll be guided, okay, which to work first, okay, the X components or the Y components, and then later on solve for the net force. Okay, so let us recall the normal force. Again, normal force is force perpendicular to the surface of the object. So say for example, we have here this box. Okay, so if we'll have this box, okay, so it has its weight pointing downward. Okay, and this is the normal force. And our objective will be talking about flat surface first. Flat surfaces. Of course, normal force is still act on inclined plane, but the limited discussion will have first the flat surfaces. Okay? Okay, for you to compute for the frictional force, you have this formula. Okay, but what is frictional force? Remember that we have mentioned this as part of the contact forces, because of course, when there is frictional force, this means that there are two surfaces in contact. So here, force resisting the relative motion of the surface. So if an object is moving, of course, see for example, you have this ball, okay, moving towards this direction. Okay, so the motion of the ball is towards this. So that is the motion caused by the applied force. So therefore, your frictional force is here, opposite the direction of the motion of the object. Okay, this applies to solid surfaces, fluid, or any material that are sliding against each other. Okay, so here, for you to compute for the frictional force is equal to the mu. This is a Greek letter mu, okay, which means the coefficient of friction, multiplied by the normal force. Of course, this is a force, so its unit is in Newton. Okay, let's talk about coefficient of friction. When we say coefficient of friction, this refers to the stickiness, okay, to the stickiness of the surface. Okay, how much is the ratio between the frictional force and the normal force. Okay, and then we have the normal force, of course, for flat surfaces. Remember that this is for flat surfaces. Okay, I have to really emphasize that this is for flat surface, because if we'll talk about inclined plane, so there will be another formula for the normal force for inclined plane. Okay, so this is your weight and this is the normal force. Okay, so for flat surfaces, most cases, normal force is equal to the weight, equal to the mass times the acceleration due to gravity. So if you wanna, if you will be simplifying this formula, you can also have here, of course, that is mu sub Fn. Okay, let's have this. Okay, so substituting the Fn, so your frictional force will be equal to the coefficient of friction multiplied by m times g. Okay, so this is for flat surfaces. Okay, next. Okay, so we have two types of friction. We have here the, oops, row, yeah, static friction and the kinetic friction. So when we say static friction, this occurs to objects that are at rest. Okay, static energy is for objects at rest. And for kinetic energy, this is relative to the motion of the object. So this is for moving object. Okay? Okay. So here, for static friction, there is no relative motion, of course, because it's at rest. Okay, so static friction will resist the motion of the object. Okay, so of course, it will maintain the object in its condition, which is at rest. For kinetic friction, this resists the motion of the object. So this is the one that causes the object to, for example, a rolling ball. Okay. If the ball is rolling, then it will suddenly stop at this point. This is because of the kinetic friction. Okay, so then if it will start to slow down because of the kinetic friction acting on the ball. Okay, so as you can see, we have the same formula. We just add a subscript, which is S for static, of course, and K for kinetic. But then basically these are just same formula. So we have F sub F. We can have F sub S. But then if it would be like very plenty of subscript, we can have F sub S. Okay, static friction is that the mu sub S multiplied by the normal force, and we have here F sub K equal to the mu sub K of Fn. Okay, why do we have mu sub S and mu sub K? Here's the thing. For several objects that are in contact with each other, so there will be different values for the static friction and the kinetic friction. So here, say for example, let's have here wood on wood. So if a wood strikes a wood, or like slides on another wood, so the static friction, the coefficient of the static friction will be equal to 0.5. Okay, while its kinetic friction is 0.3. Again, when we say coefficient of friction, or the mu, okay, so this is the ratio of the frictional force in the normal force. Okay, so that will be the ratio, so it has no unit. Okay, here's the thing for the objects that are in contact with each other. So we can see that object has a smooth surface, but in reality, if we will like look into the surface, like very zoom position or like resolution, we can see that there is this roughness in the surface of the object, especially for very rough objects. Okay, this causes the object to, of course, try to start to slow down because of these gaps. Okay, so here, if two objects are in contact, then as you can see here, these are the surfaces. Okay, surface of one object, and then here the surface of another object. If, say for example, you would like to make the object move faster, you have to reduce the kinetic friction. Again, you have to reduce the kinetic friction because you want to move it faster. And for you to reduce the friction, okay, so that it will not stop, it will continue to move, then you have to fill in these gaps. Okay, you can do that by, for example, adding oil. Okay, that's why when, for example, you have your door, when the door is difficult to open, then there's this friction that acts on the object, and what we do for it to be easily to be moved or open and close, we add oil. Okay, this is to reduce the friction on the object so that we can fill in the gap, and then now these surfaces can easily like move. Okay. Okay, so let's have the guided practice problem. Okay. Okay, for our guided practice problem 1, let's see. A 25 kilogram box rests on a horizontal surface. What is the minimum horizontal force that is required to cause the object or the box to begin to slide if the coefficient of static friction is 0.35? So let's try to solve this. So of course, it's important to illustrate the problem. Okay. So that you can see the forces acting in it, and do not forget to draw the FBD, the free body diagram. So we have here a box resting on the floor. So of course there is a weight. And we have here the normal force. And remember that for object at rest, normal force is equal to weight, and they're acting on the opposite direction, then therefore it would cancel out or be equal to 0. Okay? So here for our force, the question is, how much is the minimum horizontal force required for you to move in? Of course, that will be the frictional force, which is the static friction. Okay? So that refers to the amount of the static friction. Okay. So let's write the given. For our given, we have here the mass equal to 25 kilogram. And we have the coefficient of the static friction, that is mu sub s equal to 0.35. 0.35, walang unit. Okay? So this is just like a cursive letter U, a small letter U. Okay? And it's not letter M. Okay? So we are asked to find, again, we are asked to find here the frictional force, or the static friction. Okay, static friction. So for the static friction, for its value, for it to start to move, okay, so static friction, okay, there, okay, so there are a lot of rooster outside, and okay, so let's write the equation. F sub s, or the static friction, is equal to the mu sub s multiplied by the normal force, which will be your of course mu sub s multiplied by mass times the acceleration due to gravity. And then let's just substitute the value. We have here 0.35 multiplied by 25 kilogram multiplied by the acceleration due to gravity, 9.8 meter per second squared. And that will be equal to, okay, so where is that cursor? Okay, so this will be equal to, okay, so that will be equal to 85.75 Newton. So here's the answer. Of course, this is your solution. Okay, so this means that you need 85.75 Newton of force for you to make this box move, start to move. Okay, so that's it. Okay, let's have number 2. Okay, for number 2, we have here a 25 kilogram box rest on the floor. What is the minimum horizontal force that is required to push the box across the floor if the coefficient of friction is static friction? So it should be if. This one is if. Okay, and then you're also asked, okay, to find the acceleration of the system if the person pushed the box with a force equal to 112 Newton if the coefficient of kinetic friction is 0.45. Okay, let's illustrate. There are two parts, of course. The first part is the box is resting on the floor. The second one is the force or the box which is applied or which is given a force equal to 112 Newton. So it's moving. So let's illustrate this. So first we have the box, okay, at rest. Of course, we'll have here the, okay, of course here, okay, so it should be here, okay. This is the F sub S, or the static friction. The second one is the box, okay, same box which is moving, okay. There is an applied force equal to 112 Newton, and so there will be this kinetic friction, F sub K, okay, which we're going to find, and then we'll be looking for the acceleration of the system as it moves. So let's identify the given. So here, the given are mass equal to 25 kilogram. We have the mu sub S, the coefficient of the static friction equal to 0.89. And then we have the coefficient of the kinetic friction equal to 0.45. And then we have the applied force equal to 112 Newton. Okay, so we are asked to find, first for letter A, of course, that's your F sub S. Or we can just write here F sub S, static friction, kinetic friction, and then the acceleration of the system. Okay, so let's have the equation. For our equation, of course, we'll have F sub S is equal to mu S Fn. Okay, we have F sub K equal to mu sub K Fn, or the normal force. And then, of course, for us to find the acceleration, we have to find first the summation of forces acting on the object. So that will be your F sub A minus the frictional force sub K, of course. You have to find that so that later on for our acceleration, we can now compute using the summation of forces over M. Or we can just simplify this. So we can substitute that. You can have here A is equal to, the summation of forces is FA minus F sub K over M. Okay, let's solve this one. Let's have first, let's have it here below, our F sub S. Okay, for our solution. Solution is F sub S is equal to mu sub S multiplied by the normal force. Of course, this mu sub S multiplied times mass times the acceleration due to gravity. Okay, why do we have to write this one instead of this immediately? Because, of course, as mentioned a while ago, so there are several formula for the normal force. So here, it's flat surface. So we have here 0 point. How much is that? That is 0.89. We have 0.89 multiplied by 25 kilograms, and then multiplied by 9.8. Okay, that's 9.8 meter per second squared. Okay, and this will be equal to 218.05 Newton. Okay, so that's it. Okay, so that's the static friction. Okay, but then let's find the kinetic friction. It's mu sub K Fn. Okay, that's mu sub K multiplied by mg So that will be 0.45 multiplied by 25 kilograms multiplied by 9.8 meter per second squared. And this will be equal to, of course, your F sub K will be equal to 110.25 Newton. Okay, that's 25 Newton. Okay, so the next thing that you have to do is to find the acceleration. So we'll just use this one. So acceleration is equal to the summation of forces over m or divided by mass. So that will be equal to the forces acting on that is the applied force, of course, minus the frictional force. But the frictional force is, of course, the kinetic friction, okay, over m. So let's have here the value of the applied force, which is in the given, that is 112 Newton. So minus 110.25 Newton over mass is, how much is the mass? This 25 kilogram. Okay, of course, on here you have 1.75. Okay, you can do this in your calculator already. So this 1.75 Newton over 25 kilogram. But of course, this is in Newton. We can replace it with the MKS unit. So that will be kilogram meter per second squared. Okay, so your acceleration will be equal to 0.07 meter per second squared. Okay, so that's the problem, sample problem involving, let's see, involving friction. Okay, we're able to find this. Okay, as a summary of our lesson for today, we're able to discuss the free body diagram, okay, or the FBD, drawing all the forces acting on the body, which would help you solve all the resultant force, okay, acting on the object. We were able to discuss friction on flat surfaces. Okay, the two types of friction is the static friction and the kinetic friction. Again, so for static friction, it's for object that has no relative motion or objects at rest. And then for the kinetic friction is the frictional force that precedes the motion of the object. Okay, and then we were able to solve problem involving friction. And in solving problem, you have to identify first the type of friction acting on the object. Of course, if it's at rest, it's the static, and if it's moving, probably there is an applied force, and then a frictional force is also acting in it. Okay, and then that's it. For our next topic, we'll be discussing tensional force. Thank you.